All right, you guys, you have your answers? So we're pretty much ready to go? All right, so please log on to Moodle. And there is an Excel sheet there. We are working on moving into the linear Gaussian homoscedastic IID model. And I will say that a bunch of times and even define it a couple times.
Oh, no, I see.
Do you need more lights?
Did I just download that
And don't look at the other person's answers. It's just your line. It's just your line. Yeah, there is but your line is as good as anybody else's line, and we'll show you why in a very short period of time.
I messed up on my line.
And you used a pen.
Yeah. Oh, yeah.
Here's some chalk. There it is. Are there any spare pieces of paper? Oh, awesome.
I'm coming. Don't get up. I know. Do you want those extras?
Sure, I'll use them again next year. It's just like the back version of Groundhog Day, right? Every day we wake up and go back. You can log on if you. About today, there's something that says Excel on it because I couldn't think of anything more creative for the Excel that we're doing. And it will download into something called Excel line example. I know this is being recorded, so I shouldn't read this little note that's left, but it says safety guidelines on it. So I thought you should all know. I'm only going to read the first one because it gets more absurd after that. Do not put the parts into orifices such as mouth, nostrils, ears, etc.
Oh, did you know yours?
Yeah, I'm just like, man, somebody's giving me good warnings there. All right, so does everybody have the Excel sheet up? I'm going to unbrighten it in here because I don't need it to.
Thank you.
All right, or maybe I do need a 10. Anyway, so this is the line. This is the set of dots through which you just drew a line. Okay. We are going to do the y equals mx plus b formula over here. This is the actual y and the x, but here we're going to do y equals mx plus b. Your m is your slope, and so put it in. Okay, so you just put your slope in there and your intercept. Yeah. So just to make this difficult, we will start calling the slope b from here on out. But what to do? Messing with it. So did everybody put their m and their b in? Well, I know your computer's still loading Excel. What to do? Dear Mrs. Sorry.
Okay, yeah.
And a new Apple Watch. No iPhone. Sorry, if you're gonna ask, you might as well go big. All right, so is everybody ready? Got them entered in? In the predicted, we're gonna type equals x2, which is, or a2 times m pops up, plus b, it pops up because I've already named them. And then we hit return, and we're going to drag that thing down. Okay? And yours will not look like mine because I have 1 and 1 in there, not what you have in there. And you should have a line that goes through the points, yes? Huh? You messed yours up? Did it work when? Right? And you put in the space below the I. Did you have an issue? That's because you have a mistake. All right, does everybody have something that looks a little like this? So what we just did was use the human computer to fit, and your line should be better than that, mine. But we used a human computer to regress a line through a set of points. Okay? And that line is as good as any other line, except the ones that we're going to make, because your line has the same statistical properties as most of the lines and papers out there. Because the line we're going to make here in a minute, which is supposedly the best linear unbiased estimator in a normal, of a normal variant, if it doesn't have those properties, then your line is as good as the one we're going to do statistically. All right, does everybody have this here? So the error, we want to talk about what errors are. The error is how far your line was in the y from the point. All right? So you have this error is 0, right? Because it's right on the line. Yours will not look like that because I have a different. You will have a place where your line, right, hits a dot. When your line hits a dot, the error is 0. When your line is 18 points from the dot, right, it's an error of 18. And so to get that error, here in V2, we're going to type in equals ABS. We just want how big it is, not the direction. We want ABS, and we're going to do the actual minus the predicted. And we're going to close that parenthesis. So it's the absolute value all right? It's ABS C2 minus B2. All right, and then your numbers will be different than my numbers because you have a different line. Then we're going to copy that down. Okay? And again, you will have different numbers than I have because you have a different line. Mine's not a very good line. And in here, we're going to type in equals average. And my average mean absolute deviation my MAD mean absolute deviation, right? Because error and deviation mean the same thing, so we're going to call this MAD, mean absolute deviation. Does that work? And was your MAD lower than mine?
Yes.
I would hope so. All right. Anybody get anything under 15? Okay, so you guys are sort of lower absolute deviation operators. So what if we wanted to get the minimum mean absolute deviation estimator? Google uses this. We could actually play with these numbers. So let's say I put my slope, who has lower than me? What, give me your slope.
1.
1?
Yep.
And what was your intercept?
Negative 12.
Minus 12.
Oh, no, other way. That's
Oh, you're right.
Slope. Yeah.
Oh, man. So 1
That was definitely not mine.
minus 12. There we go. So my MAD error went down substantially. So yeah, that's actually a much better fitting line. Did somebody have a different slope? Yeah?
0.56.
0.56.
Yep.
Ooh, but you probably had a bigger slope or a larger intercept.
My intercept was 6.
So we went 6. Ooh, that's even a little better, right? So we could do this. We could take yours and we could keep changing that and watching that value and eventually saying, yeah, okay, well, we'll finally, if we mess around with these long enough, write Shakespeare. No, we'll find the minimum MAD estimator, but we're going to do that. The computer actually find that for us. And so we're going to go to data and hard. We're going to go to File and Options and Add-ins and Go, File, Add-ins, Go, and we're going to check the solver add-in and say OK. Wait, could you do that again? Sure. Is it running for you all? Yeah. File, Options. There's a little button down in the middle that says Go, except on.
There it is.
It's under Tools on Mac.
It's under Tools on Mac. It's Tools Add-ins. Yeah, Tool, and then click on Solver. Tool, Excel, Add-ins, and Solver. All right. And then it should spin through, and then you'll see something over here which says Solver.
Okay.
It's doing it. There it goes.
Yeah. So.
Yeah, it's on.
Yeah.
Yeah, options open.
File. And then slide down. Add-ins.
Bryce, where did you show? You got the
Yeah, just make sure it's not in any kind of words. It's not raining.
All right, everybody got it installed? Anybody not? All right, So now we're going to click on our little solver thingy here. And the objective function that we want to set is not E21, but D21. And it's by changing the values of I2 and J2. Those still remain the same. Right? I2 and J2 are M and B. So it's going to go through and do that whack-a-mole for us in a fast and wonderful way and give us our parameters for the minimum mean absolute deviation estimate. Okay? And we should be able somewhere down here to say solve. And we're going to keep our solver solution and say OK. And so we got 0.59 and 5.46, which was pretty close. Yes?
That's not right. Your 0.6 is pretty good.
Pardon? You got what?
6.38.
6.38 is your B. Did anybody else get that?
I got something different than yours, but
Not very different? Yeah, okay. Okay, so it's gonna vary by a small amount because this is an optimizer that goes through and plays whack-a-mole and then it gets close enough. And it matters where you start because it's not an analytic solution, right? It just on mean, and it just goes through and then it gives it to us. Yeah.
What did you first put into solver? What did you put into solver first? How you
Oh, okay. It's this one. It's D21, but I'll open it back up so you can see. So I just clicked on the D21, which is my mean absolute deviation. And then I left everything else the same, the I2. And this goes through and solves for us.
So you didn't put anything in solver?
It's just the D21, the minimum, and the I2 and the J2. Are you not seeing the I2 and J2 in there?
Yeah, with the dollar signs?
Yeah.
Okay.
And the dollar signs just means that it absolutely stays in that place. Okay? And then solve. And okay. All right. So that gave us an estimator known as the minimum mean absolute deviation estimator. Okay? Which has become a little bit trendy of late, but that's not the one we're going to use. We're going to use something called the minimum mean square error estimator, which is a little bit more work. Okay? This one is fine. It lacks some statistical properties that people like, but it tends to do a pretty good job if you have to do projections. But now we're going to do the square here of our error, squared error. I hope I put squared error up there. So we're going to do the squared error, which equals, in parentheses, the predicted minus the actual squared. And we're going to copy that down. Okay? And those are our squared error terms, which are also all positive. Okay? And we're going to compare this to how well we would do if we just knew the mean. Okay? So if we just knew the mean of y, what's our error from the mean of y? Okay, we call it the total error, but it's just the error from the mean of y. And that will be equals the predicted minus C21. But we're going to put dollar sign, whoops. Let me do that again. Predicted minus the average of y, C21. I'm going to select that and put dollar signs on it. And I did that by hitting the F4 key. So it's and when we drag that, that just means it's going to keep. When we drag that down, you'll see what happens. All right? And we're going to square that as well. Okay?
Yes. That's all.
People able to get that formula in? And then we're gonna, your number might be slightly different than mine. And we're gonna slide that down. And you'll notice if you go down, you'll notice how the dollar sign keeps it from moving, right? When we slide it down by not having anything there, we get relative referencing by how the dollar signs. It's called absolute referencing. Question?
I don't know what happened, but I lost everything that we just did.
All right, give me just a second here.
Thank you. I don't know what I did. I know.
Okay, see if you can get it and put it up.
Got it. Thank you.
All right. I know public shaming isn't allowed anymore, but you still have to do it.
It's okay. I accept it. You're welcome now.
All right. So now we have our total total squared error. We haven't totaled them here, so we're just going to go down there, go to home, and just total those. And all right.
Can you do that again?
I clicked up at the bottom, and I clicked on home, and I clicked the sum key, and I did that again over the underneath the other one. Yes. Are you raising your hand or just doing it? Louder.
Was for a little while.
Okay. Yes.
There you go. Probably just way down.
Try hitting the F9 key. Otherwise, you might have too many dollar signs. Yeah.
I knew it was early actually, but I didn't know it
right, are we pretty, so we understand what the squared error is? It's just, right, it's just the error, it's just the difference between the line and the point squared times itself. All right, so they're nicely all positive. So we don't have to be in the imaginary world where I usually live. And we want, instead of minimizing our mean absolute deviation, we're going to do the minimum sum of squared errors. Okay? The minimum SSE, or the minimum sum of squared errors estimator. All right? And that's, or we could call it a guesstimator if you want. So we're going to go to data and solver, and instead of D21, we're going to do E21. Okay, and okay. And our line changed slightly. Yeah? Just a little bit, because the difference between the minute SSE and the minimum amount estimator is just this much, a little tweaking. Does everybody have something pretty close to 50368 and 5.9832? Okay, so yeah, and so now we have, and what are our coefficients? What does that line look like if we had to write that? Y equals mx plus b, that would look like plus 5.4-ish. What is it?
5.9.
5.9. All right. So 0.50 plus 5.9 plus error. Right? That's our actual point. So this is our line. Sorry. Forgot lunchbox. High food. He's got a school account, you know. And after my lectures on food safety and school cafeterias, he won't eat there, but I don't mind. I wouldn't. All right, so please. But you guys have seen me eating rotten tuna fish sandwiches, so. All right, so some of you. Right click, please, click the dot, right click and do add trend line. Click on the dot still selected, right click and add trend line. And linear is fine. And we're going to add display estimation and display our square value. Okay? All right, clicked on the dots. I right clicked on the dots, 2 fingers and a toe on a map. I don't know, it's different for every map. And then we're going to close, and it should pop up here where we can't see it, so I'm going to close my format trend line, and I'm going to move that out so I can see it. And I'm going to go to home, and I'm going to make it like 18, except I missed. All right, so it comes out as, wow, amazingly similar. Yes?
So what exactly does that R squared value mean?
The R-square value is the proportion, it is, if you take all of the squares, and I have the formula wrong here for some reason, I'll have to look it up. It takes all of the squares in the distances between that, what proportion of the total amount is explained by the line. Okay? So how much different is that squared error to the total? Okay? I have an error here which I have to think about why. Because my r squared turns into r squared. All right, so I'm gonna have to steal my computer. Give me this. And for most of you, you can't see it because it's identical. All right, so while I'm waiting for this to come up, do we understand what a regression line is? A regression line is just a fancy version of any line we drew through there that sort of minimizes some criteria. All right? Yours was the what looks good to me criterion. The first criterion that we used was absolute deviation. The second criterion we used was sum of squared errors. Okay? The magical thing about sum of squared errors is that it maps nicely to it maps nicely to the normal function. What numbers are you guys getting here? Yeah, so let me see what my total error here is. Oh, sorry, C2 minus C21. All right, take it, it's C2 minus C21. And you gotta have the dollar signs on that. I don't know why. Okay, so what the R square is it's 1 if it's a perfect fit, it's 0 if that line is completely flat and on the mean, and somewhere in between. And it is the percentage of the total model error with the sum of squared errors. So it's sum of squared errors over total model errors. Okay? And that equal, and 1 minus that is the R squared. And that is a measure of fit. So it's how well did we do. The closer to 1 that is, the closer our points are, our line is to the points. Does that make sense? All right. So if we went back to our old values, so I went back to 1 and 1, right? It's so bad, right? It's so bad, it's not even in the range I said it should be, but then, all right? Because it's not even inside the mean range, all right? Does that make sense? You understand what we just did? All right, so this is the linear model. It's linear because it's a line. It's Gaussian because when we put this line, when we do the minimum squared errors through this, the distribution of these errors should look like a Gaussian distribution. It should look like a bell curve. Okay? And we should be able to take our errors, well, these are error squares. So let's go ahead and click on D, right-click on D and insert, and let's call that error square. And here we'll just call this error because we're not going to square it.
We already have an error.
We already have an error squared.
You have it and I don't?
No, you do
It's called
too.
squared error.
It's because you have your.
Oh, because I have
columns lined
ABS,
up.
right, okay, sorry. So let me just get rid of the ABS there, because we want the, because we don't want the ABS. Go ahead and get rid of the ABS and copy that down. And it should, as if by magic, be almost 0. Our sum should now be 0. So I just took out the ABS in the error, which I should have retitled absolute error, but I just took out my ABS and copied that down to save a smidgen of time. Okay? And so I now have all these errors, positive and negative, some above the line, some below the line, and the average is a very small number. It should be close to 0, right? Is that a small number? Pretty small number. Okay, and we're going to go ahead and select all of those, and we should be able to insert, oh no, we'd have to install one more thing. Let's give it a shot since we know how to do that. All right, go to File, Tools, Options, Add-ins, Go, and turn on the Analysis Tool Pack. Mac people, you might not have this. Regular one.
What if we don't have that tool?
Watch for a minute. We're not gonna do this. Excel is not the greatest place to be doing regression analysis, but I'm just showing you that you can. All right. And we're gonna hit OK. And the input range for our histogram is going to be our errors. And chart output, we're going to select our errors. We're going to let it pick the bin. We're going to hit a chart output. And we should be able to say OK. All right, and if we had a large sample size, that would be normal. We have a small sample size, so it is not. But in theory, it is. It should be normal around that point. Adding to 0 is the first thing. And yours is going to be D2 to D20. All right, so that error should be distributed 0, and we just did the standard deviation for a population. And that's our distribution. It should be 0, 14, mean and variance. Okay. Which should look something like that's a minus, this is a plus. All right, it should look something like that. That is what our distribution should look like. We only have 20 points, so we're not going to trace out a normal distribution with only 20 points. Okay? Let's go ahead and leave this open. Click the save button. I don't mind uploading, but. So let's go ahead and open R. And our commander. Not really. Just go ahead and load it up and then go to distributions, continuous distribution, normal distribution, plot normal distribution, and we're going to put 0 and 14 in there. And okay. And that's what our normal distribution of those errors should look like. Okay. So the assumptions that we have that make the things, the p-values, because this is normally distributed and therefore the parameter values are distributed t. For this to work, this e, this error term here, needs to be distributed 0 and variance, mean and variance, but it's got to be 0 and sigma, okay? And there's some properties of sigma that we won't get into, but it has to be normally distributed. So when it creates a chart, it needs to have a chart that looks like this, all right? Is ours distributed around 0? Were our errors distributed around 0? Yeah. Did it look normal-ish? No-ish? Okay. This turns out as n goes to infinity and beyond. All right. So these assumptions sort of are supposed to fit with small values, but they rarely do with small values. I mean, you got 20. It's got 20 points, the chances of them actually hitting a normal clearly are not going to happen well. So we're gonna, does this make sense? You understand what I mean by when I say error now? When I say error, you understand what I mean is the distance between, in the y, that line and the point. That makes sense? And that we need these errors to be well behaved before, because if it's not, if it doesn't follow this distribution, then the p-values for however far out, then our p-values don't work, right? If it doesn't follow this distribution, then our p-values don't work. That makes sense? Because it's a probability distribution, and everything we do from here on out, and have been doing, has a probability distribution. If our model does not fit the assumptions, then we can't trust the probability distribution. We can't trust our p-values very much. All right, so let's go back over to Excel, back to sheet 1. And we're going to go ahead and do, and just select A1 through C20. And we're going to copy that. So we selected A1 through C20, and we copy it. And Mac people, this might not work, but I hope it does. And we're going to go to Data, Import Data from Text File, Clipboard, or URL. All right? And we'll just call it data set because it's just a fake data set. Or if you want to call it fake data, you can do that. And clipboard and tabs. And OK. And it should now be in here with X predicted in actual. Did that work for Matthew? All right. Everybody have the data in? All right, do you guys want to take a 5-minute break now and then finish off at 10:50, or do you want to push on and finish up about 5-10 minutes early? Push on. All right. You're the kind of people who doesn't not have to take a rest. All right, go to statistics, fit model, linear regression. Doesn't matter. We're just going to do the linear regression because it's just what we did. And our response is Y, and our explanatory is X. Our response is Y, our explanatory is X. We'll say OK.
Look at that.
Would you look at that?
It's a lot faster.
Yeah, a lot faster. And here we have an estimate of 0.5037 that has a standard error of 0.12, and we're going to map what that looks like as a probability distribution, which is a t-value of 4.155, and that's significant. All right? But we're going to go to models, graphs, and effects plots, and OK. Lo and behold. Okay, you put a smoother one in there. Did that work?
I got the lines and not.
Yeah, I can get this squiggle.
Oh, that's because I put did the partials. I'm sorry, I clicked, but I didn't speak. Models, graphs, effects, plots, and I clicked the plot partial residuals. And okay. All right. And if that squiggly line, which is called the lowest fit, which is just a linear regression that moves around, if it's right along the line, it means that you're probably linear. If it bounces around the line, it means you might not be. Okay? So, it's a little easier than doing it in Excel, just because. And there's some other things that we can look at too here in models. There, we can add observation statistics to data, so we're going to do that. We're going to go to model, add observation statistics to data, and we're going to get rid of all the rest of this because I don't want to talk about it right now. And we're going to leave that with residuals, and we'll say okay. Okay, and then we're going to view our data set. And we see our residuals are in fact our predicted minus our actual. All right, so we see it's just the same thing. We're going to go to graphs, and we'll do a density estimate of our residuals. I'll do that again. Graphs, density estimate of our residuals. And not particularly normal-ish looking. All right, which is this is just the same as the histogram, only it's smooth. All right. So we didn't get something that looks particularly normal, which makes me truly upset because I told you that for all of our probabilities to work, these had to be distributed normally. They don't look like they're distributed normally, so I'm starting to feel sad. So I'm going to go to my statistics and summaries. Statistics and summaries, and there's a test of normality. So I'm going to ask if my errors are normal. And I'm going to click on my residuals. And Shapiro-Wilk is as good as any of the others, but you can click any of the others because most of the time they give you the same result. And so we're going to say okay. And, thank goodness, we're only a little non-normal, right? Our p-value is 0.07. If that p-value is significant, we reject normality. Does that make sense? If that p-value is significant, I can't reject that the e's are normal, are non-normal, right? Because there's really not enough points to reject it. Does that make sense? You understand up here? Right, that 0.07 is not less than 0.05. So it's a little non-normal, but it's not a lot non-normal. Okay? We could go to statistics, test of normality, and let's try Anderson-Darling. It's 0.07. Let's go to statistics, summaries, test of normality, Kramer-von Mises, 0.08. You can notice the trend here. Okay. All right. So if you're in that sort of kind of range where it might be a little non-normal, choose a different test that gives you the result that you like. This is known as That's a K, it just looks like a K and an R got together. All right, this is known as p-hacking, which you go through and you do a whole bunch of different tests that test roughly the same thing, and you pick the answer that you like best. And again, we can read up on the test as to which one is the most appropriate in different cases. But all of these give us exactly the same result, is that we're a little bit non-normal, and we don't have to really worry about our p-values on our t. Let's go to our distributions, continuous distributions, t-distribution. Plot the t-distribution. How many degrees of freedom? Does it say in our output? $17, thank you. I can't use my mouse today to save my life.
How many degrees of freedom did you use?
17, because it tells us that in the output. Slide up and it says,
I see it.
oh, and our residual standard error was 14. So lovely when it all works out. All right, so 17 degrees of freedom. Is 4 a long ways out? What was our t value? Our t value was 4.155, which means we come out here 4.155, and we sum. You see this? So like if you summed everything from here over, it'd be 50%. This whole thing sums up to 1. If you summed everything that way over, it'd be 50%. If you sum from here to there, from the beginning to the end, it's 1. So from 4.155, there's how much left? What's the probability that happened by accident? And that's what this means. We would get a t-value of 0.155. We would get a t-value of 0 50% of the time. We would get a t-value of plus 4.155. And how often did it tell us that was? About 1 in 1,500 times. Okay? So, not very often. So we're close enough to normal that we're not going to get upset, that we can now say our p-values are close enough. Our p-value is huge. Anyway, our effect size is huge, so we don't really have to worry about this, and we can trust that our line is a good one. All right? That makes sense? We can go to our model and we can hit basic diagnostic plots. And these diagnostic plots also tell us something about, and we're only going to talk about the top two. These are our fitted values. Those are the predicted values that we did. And these are the residuals. Okay? This should not have a slope or a shape. It should not look like a trumpet. It should not look like it has a waist. It should not go up. It should not go down. Does this look like it has a shape? Does it look like a trumpet? A little tiny bit. Does it have a slope? No, I mean, it looks like it could go down a little bit. For the most part, it's pretty flat. If this has a shape, we have something called heteroscedasticity, meaning that we don't have the equal variance. And when I say IID of these E's, the assumptions are Gaussian and identically and independently distributed. If these have a shape, and if they don't fall on this line, then they are not Gaussian. They're not normal. We ran the test for that. And if they have too much of a shape, if it looks like they like follow an S-curve or something, and all there looks like there's some sort of relationship amongst the residuals, then they're not independently distributed. Okay? So we look at these charts and we don't see these things fall mostly on the line. And this doesn't really have it might have a little bit of a shape, but not clearly noticeable. All right? So now we are happy with we are now happy with our linear, normal, or Gaussian homoscedastic model because we tested it. It doesn't have a shape here that's really too bad. It's pretty normal. Okay? Is this making sense? These are new terms, I'm sure. But the reason that we go through and we care about these terms is that if we're going to p-hack, we should do it accurately. But if these assumptions are, none of them are particularly violated, then we can trust our t-values. And if we can trust our t-values, then we can do science and say that line is a significant line. All right? If these don't fit, then maybe that result doesn't fit. So the reason we test assumptions is something that's not done a lot in undergraduate courses. But it turns out that when you get to trying to publish in graduate school, you spend a lot of time, months and months and months, getting your models out, and then some jerk professor will say, did you test the assumptions? And you'll have this look on your face saying, oh, I was about to do that. And you do, and your assumptions don't fit, and then you get to do 6 more months worth of work. All right, so we will always look at our assumptions to see what we have. All right? We're not going to do anything more, because that's a lot, and we will come back to this on Tuesday, and we'll go through this process again with some real data. I did it with small fake data, so you could get a handle on it. We did it in Excel, so you can see what's going on behind the scenes, which is the minimization of a function that you care about, the MAD or the minimum SSE. There's